Hi everyone, my name is Xiaoyue Lin, but you can also call me Daisy. Today I will be discussing performance engineering, an essential aspect of software development that helps ensure systems perform efficiently and reliably. Performance engineering goes beyond merely testing software. It's a proactive approach that seeks to build systems capable of meeting performance demands right from the beginning. To start, let's consider a fundamental question. What is performance? Pause and think. How would you define the performance of a system? What characteristics would make you consider software well performing? In software, performance refers to a system's ability to respond quickly to user interactions, manage multiple requests seamlessly, and scale efficiently as demand grows. Key metrics like latency, throughput, and resource utilization are crucial here. Each of these metrics affects how the end user perceives the application. For instance, latency impacts how faster a user sees the result after they make a request, while throughput relates to how many tasks the system can handle simultaneously. Resource utilization, such as CPU and memory usage, affects how well the application runs without crashing or slowing down under heavy load. Together, these metrics ultimately influence customer satisfaction, business outcomes, and even profitability, as slow or unreliable systems can lead to customer drop-off. Now, we have a basic understanding of performance. Let's explore performance engineering. I listed three definitions for performance engineering here. One common point of them is performance engineering applies to the whole development lifecycle. Now, let's focus on a basic idea of performance engineering. Performance engineering is a proactive, continuous, and collaborative approach practice to testing and monitoring software performance throughout the software development lifecycle. This field involves the methods, techniques, and strategies used to ensure a system meets its specific performance requirements. The goal of performance engineering is not just to detect issues, but to prevent them. Designing systems that are robust, efficient, and scalable from the outset. This proactive approach is especially critical in today's digital world, where users expect instant response and uninterrupted service. Performance engineering is about embedding performance into every phase, ensuring that systems are reliable under any foreseeable condition. It's easy to mix up performance engineering and performance testing, but they serve different purposes. Performance testing typically occurs toward the end of development and focuses on identifying how well a system handles different loads, often revealing issues like slow response times or bottlenecks. Performance engineering, on the other hand, is a proactive, holistic approach. It integrates performance considerations into every phase of the development lifecycle, from planning to design to development, testing, and deployment. This approach allows us to anticipate potential issues and address them early, instead of merely reacting to problems. Performance engineering empowers teams to make informed design choices that can prevent issues, improve reliability, and lead to better user experiences. So, how do we integrate performance engineering into the software development lifecycle? This begins in the requirement phase, where we establishing performance goals, such as load capacity and response time targets. In the design phase, performance consideration shapes the system architecture, leading to choices like microservice for scalability or caching mechanism for faster response times. During development, engineers work to optimize code, and in testing phase, we conduct load, stress, and endurance tests to simulate real-world conditions. Finally, after deployment, continuous monitoring ensures that the system maintains its performance standards. Each phase plays a role in building a resilient system, and performance engineering brings them together as a cohesive process that ensures consistency in delivering high-quality performance. Now, let's look at some common performance optimization techniques. These optimizations can occur across various parts of the system. Caching, storing frequently accessed data to reduce retrieval times. Data optimization, using indexing and efficient queries to improve database performance. Code profiling, identifying and refining slow or inefficient code. Scaling, adding resources through horizontal scaling or vertical scaling. It's also essential to remember that nearly all key performance indicators influence each other. For example, you may use memory to cache data for faster access, but this also consumes memory, affecting capacity. Pause and think. Can you think of additional key performance indicators beyond the common techniques mentioned? Because of hardware limitations, it's critical to view all key performance indicators as part of a whole system rather than focusing on one in isolation. Or over-optimization, a single key performance indicator could lead to unintended negative impacts on other performance metrics. For instance, prioritizing response time will lead to higher CPU usage, ultimately causing system instability. This interdependence is why a balanced, holistic approach to performance engineering is so important. Now, let's look at some tools that support performance engineering. Tools for performance testing, like JMeter and Gatling, simulate user load and help identify bottlenecks, enabling teams to optimize their systems under realistic conditions. Application performance monitoring tools such as New Relic and Datadog offer real-time visibility into system health, resource usage, and response times, helping teams detect and respond to issues promptly. For infrastructure monitoring, Prometheus and Grafana are popular choices, especially in cloud environments, where they help ensure resources are allocated and utilized efficiently. Choosing the right tool is essential for effective performance engineering and continuous monitoring, as these tools provide the insights needed to understand and improve system performance. In conclusion, performance engineering is a tool for building scalable, efficient, and user-friendly software. Unlike traditional performance testing, which usually occurs at the end, performance engineering integrates performance management throughout the entire development lifecycle. By combining strategic planning, optimization techniques, and the right tools, we can ensure our systems not only meet but exceed performance expectations. The ultimate goal is to create seamless user experience, where users interact with fast, reliable, and responsive software. Thank you for listening, and I'm happy to answer any questions you may have.